All right, hey, welcome here to our first magnetism lab. And I'll go ahead and open up my lab manual and encourage you to launch your PDF and go to page 30. And let me kind of explain the background of this. But one of the things I hope you're getting out of chapter 29 and also 30, that there's a lot of parallelism between the electricity and the magnetism. And so kind of the things we learned about electricity, we can carry that forward to our magnetism. And hopefully it'll make our learning a little bit easier. And see, and one of those things was way back, when we first started this class in chapter 23 of Survey, we learned about charges. And we learned that if you had a charge, it would create around it a field. And as you moved away from that charge, the field would decrease, and we called this the 1 over r squared law. That is, as you moved further away, it decreased according to this 1 over the distance squared. You might even recall this was the second lab we did. The very first lab, you might remember, we had like those vinyls and acetate strips, and we were rubbing them with wool and with paper, and we would rub them and we would look at the effect of the charges. But on the second lab, we had this big silver ball. In fact, it was right here on the edge of this table right here. And we had this little probe, and we moved it across, and we measured the strength of the electric field. And we called this the 1 over r squared for electricity. Because today we're going to do the same thing. This is called the inverse square law of magnetism. Now, the one major difference, there's a few minor differences, but the one absolutely important and major difference between magnetism and electricity is there's no such thing as a single pole. There's no monopole. So, in order to measure the field, we have to do something a little clever, a little tricky. It actually is a fairly easy lab to collect the data, but it's a little tricky to understand why we're doing it the way we do it. And so I want to take a few moments here at the beginning and just kind of explain what your author is trying to say here in words on this first page 30 and then page 31, where he says, look, how are we going to measure the field from a single pole if we can never have a single pole by itself? And it's, I think, a fairly interesting and tricky move on the author's part. And so we are going to hopefully see that if we could, and I'll say it again, we can't, but if we could get a monopole by itself and we measured its field, we want to then see if the magnetic field from a monopole would drop away with a 1 over r squared value. And so we would have the same law of magnetism as we do for electricity. And of course, you'll see that the answer to that question is yes, it is. So let me grab your attention. Maybe I'll draw you on the far part of the board here, because the object we're going to be using is a compass. And in a moment, I will show you the equipment. The compass will look something like this. The magnet itself, the compass itself, is a small piece of metal, about this big, maybe a centimeter or two. When I walk over and show you the equipment, you'll see that. And what we would like to see is how the field would change if you had a monopole. But there's the trouble. I don't get a monopole here. And also if I had another magnet, and let me just put a magnet over here. And so North Pole, South Pole. This right here, this North Pole is making a field. And it is affecting this compass. And so what we're going to do in today's experiment is change the distance between the field we want to measure. We want to measure the field from this North Pole here. And of course, we will measure it by see how it affects this compass. Now, here's the first bit of equipment. In order to measure just a single pole, we're going to use a magnet that is over a meter long. And this is going to be our little tricky way. And then there's another little tricky I will show you in just a second. But this south pole will be a meter further away than the north pole. And the idea being here is that even though we can't create a magnet with just a north pole, perhaps we can make a magnet where the south pole is far enough away that we can see that effect. Okay, and so let me just walk over here to your equipment, and you'll see what I'm talking about. I'll start right over here, down here on the table, because I'm going to run the experiment right down here on this table, because my teacher's setup that I usually do it on has a bunch of rebar underneath it, which is very magnetized. But these student tables are all wood, and so I moved over to here where the students would normally be working. All right. Well, it looked like Ron was pointing down at the compass, and so you'll see this little metal piece that's kind of pointing in this direction. There's kind of a, it's not really blue, kind of a sea green, if you will. That's pointing to the north, and the other side is pointing to the south. And then we also have these long arms sticking out. I didn't put that in my drawing, but when I go back to the board, I'll put it in my drawing. And they stick out, and they have these long arms that then can go along a protractor, so I can kind of measure how far they've moved. And so that's your equipment. So this is the compass that I'm talking about. Now, the big long magnet, let me show you that over here. I don't want to get it too close to my compass yet. But this is the big magnet. And so down here is a north pole, and way up here is a south pole. And so that's what I was saying earlier, that our north pole and our south pole will be a meter apart. But also, I'm going to mount it in a vertical fashion. And at the risk maybe of getting too close, let me kind of show you the setup. I'll get maybe about this close for starters. But by having it in a vertical position, the pole I don't care about, the south pole, not only is it further away, but it would be forcing the compass to rotate in a downward direction, which this compass can't do it. So not only is this south pole far away, but it's in a position that would force the compass to twist in a way it can't twist. It can only twist in a horizontal plane. And so that's why my north pole is going to be down here in the same plane as my compass. And the north pole I'm going to put, like I said, not only far away, I'm sorry, south pole, not only far away, but also at an angle that is hopefully not possible for affecting my compass. So with that in mind, I'll come back to my drawing. And I suppose I would argue that my drawing then is a poor drawing, because I've drawn it like the south pole is in the same plane and far away, when in reality, let's see if I can kind of redraw this, it's more like this. My north pole, so I'll put north, is going to be in the same plane as my compass, and then a meter away, and kind of going into the board here, will be my south pole. And all of that is to then say that if I'm clever enough, the effect of the south pole will be minimal enough that I can then have the effect from this north pole. And as I move the magnet different distances, so I'll call this R, I'll be able to see how a monopole, it's See, there's the trouble. Can't actually get a monopole by itself. How a field and its force field against this compass. Okay? And so that's, like I said, kind of the cleverness of this experiment. So I kind of like it because of that. Okay, now with that in mind, maybe I should add another color here, maybe a couple different colors, because the other two big challenges, as I was mentioning here, is that this compass then also has two poles. And so the North Pole on my compass will be repelled from this North Pole. And so as I get closer, it will start pushing, if you will, this North Pole away. And likewise, it'll trap this South Pole. And so I need to consider both poles and the effect of both poles on this compass. Because I would say the compass, the two poles are close together. So it's not like I have a monopole next to a monopole. I'm doing the best I can to get a monopole for this one, but it's going to have an effect on this dipole. Now, fortunately, as you'll see, the same effect it has on the North Pole is the same effect it has on the South Pole, at least almost. I realize that the South Pole is a hair closer than the North Pole. And so I'm going to make this one have two poles, and I'm going to make it small. Whereas this one, I'm going to make a North Pole and make it big. And so that's our setup. We've got a big magnet here and a small magnet here. Now, the other thing to keep in mind is, besides the magnetic field from the one I want to actually measure, there is what we call the background magnetic field. I think, as you already know, the Earth has a natural magnetic field. In addition to that, inside of this building, we have a magnetic field because of the steel and the rebar that it makes this building. So I'm going to put those two together, and I'll just call it the background field. Maybe I should just call it the Earth's field. Yeah, I'll just call it the Earth's field. But it really is more than that. It is the Earth's field and the rebar. But the rebar is kind of small, as you'll see. We make a measurement. They even ask you later on to figure out what the strength of the background field is, and they call it the Earth's magnetic field. So we're going to get a chance here to actually measure the Earth's magnetic field. But I think a better phrase is it's the background field. It's the Earth and the building's rebar. Could even be a little bit of our mountains. Our local mountains are very magnetic. A lot of iron in them. And so we have a local effect that again, you might call that the Earth. But again, I'm just going to incorporate all of them together and call them the background field, but I'll also refer to them to the Earth's field because that's how the author of the lab manual does. A little careless, but does nonetheless. Okay, so watch this. As you just saw, the compass I have has this long needle sticking out, and I am going to initially start it so that it's reading at 0 degrees. That would be saying, without this magnet around, there still is the background magnetic field. There still is the Earth's magnetic field. And so maybe in an orange color, I'm going to do this. The Earth's magnetic field, and I'll say force from the Earth, or if you want, force from the background field, would be pulling it in that direction. That's why when I don't have my magnet for my experiment, when this is far away, this compass will settle in a direction that we would call north. Okay, and so I've got the north magnetic field. In fact, to show you that, so I didn't have to walk all the way back to the equipment, I brought this little compass out because I think I can kind of tilt it a little bit without having too much of an effect. And it's still got this blue tent pointing that way. So there's the direction of the background field, the Earth's magnetic field in this room. And, well, looks like if I tilt it, I change it, but it's kind of this way. And then, of course, this is the south. So that direction is south, and this direction is north. And if you don't have any other magnets around, the compass would point in the magnetic north direction. It's when I introduce this other compass that things begin to fight each other. So here's what I'm going to do. I am going to bring the magnet that I want to measure. This is the goal of the lab. How does the magnetic field change from this magnet? We know it's going to be really strong when these two are close and then taper off as we move it away. But hoping you'll see here, if I draw this in red, is that there would be a force, and I'll call it F magnetic, meaning the force coming from this magnet. Did you notice the setup then? I have my magnet on an east-west axis. And so in a moment when I get to the equipment, I will make sure that as I move my magnet, I will be moving it along a direction of east-west. Okay? And I think I will start with it moving it west, and then I'll start with it close, and then the second time they say start with it close and go east, although I guess this would be the first one. I'd start here and move away, that'd be west, and I'll start here and go that way, that would be east. So that's what we're going to be doing here. But so that you can understand this, when I bring it close and this turns a little bit, this needle will be now pointing at some angle. And that's why I was showing you the equipment here. The compass will then twist, and we'll see this needle move to some angle theta. And so if I draw that up here, it would look like this. There would be an angle theta. And of course, at this particular location, once it settles down, here's what we would know. I'll just redraw the force from the Earth's magnetic field, and then the force from the magnet that I'm using. And when this compass settles down, and of course now we got to go back to physics 121 here for a second, we would know the torques are equal. And so if I can then write here that the torque from the Earth's magnetic field and the torque from the magnetic field that I'm creating, or maybe I should say we are creating because we're partners here, okay, so what I'm creating will then be equal. So let me go one step over here and remind you that the magnitude of the torque is the magnitude of R cross F. And so this takes us back to physics 121 and torques. And the magnitude would be the magnitude of R times the magnitude of F times the sine of the angle between them. Okay, so let's apply that over to here. So if I put an R, an F, and a sine phi, and over here I put an R, an F, and a sine of phi, let me just be careful because these are not necessarily the same r's, the same f's, or the same phi's, okay? This is the angle between them. So let's look at the Earth's magnetic field. So if I come over here and I look at the torque on this compass, and I call the distance from the pivot point on the compass to the monopole out here, if I call that L, then I would say the R is the L. Okay. Now, the F is the force I get from the Earth's magnetic field. And I hope it seems reasonable to you. I didn't say this, but as the compass turns, this compass is so small that when it turns, it really doesn't get any closer to the North Pole. And so the amount of force from the Earth stays the same, really no matter how much I turn the compass, and no matter how much I bring this one close. So this is a constant force regardless of where the compass is. Now, the angle here might be a little tricky, and so this right here would be the L, and so that's the R vector. This is the E, and that's the angle between them. But I'm hoping you see the angle that's is the same as that, which I've called theta. So the angle phi here, coming from my just physics 121 process, would be this angle phi, theta. And so I'll just replace this phi with that theta. Now, the other side of this equation right here, this R, and this F, and this angle is all about the magnetic field and the magnetic force coming from my magnet. So again, the R would still be this same distance, L, okay. The F would be the force coming from my magnet. So here's my magnet pointing this way, so there's the magnetic force. And the angle between them would be this angle right here. And so if this angle theta, and I have my magnet on the west line, then this would be 90 degrees minus theta. So this over here should be 90 minus theta. Okay. Now, I can simplify this a little bit. The first thing I can do is to recognize that the L's are the same. Maybe while I'm thinking about it, I should point out that everything I just did for the North Pole is also true for the South Pole. So technically there's a force this way from the force from the Earth's magnetic field, and then there is a magnetic field, a magnetic force from the magnetic field of this one. So you might argue that this torque really should be doubled, and that this torque should also be doubled. All right. So maybe to make it a little more complete, I'll make sure I include those two. But again, that doesn't change ultimately what I'm after. I just doubles the torque on each of them and they cancel off. The two big things I want you to see are here. I'll leave the force of the Earth alone for a moment. I'll leave sine theta alone for a moment. But these are the two things I want to look at. I want to say this, that the force coming from this magnet should change with distance, and I'd like to discover what that is. That is the point of this lab. So let's write it this way. Let's write it as some constant times the distance away that the magnet is, r, raised to some power. And so I'm suspecting that the magnetic field should decrease as our magnet gets further away. In fact, the title of the lab is the 1 over r squared, or the inverse square law of magnetism. So I suspect that this n right here would be a -2. I suspect that if magnetism follows the parallel of electricity, then the magnetic field from a monopole would taper away with a 1 over r squared value. So we're going to collect some data here in a little bit, and we're going to see if that's true. And so that's really the goal of this lab, is to show what is the value of n and hopefully get something close to -2. Okay? So that's how we are going to find the distance behavior of the magnetic field from a magnet. Okay, now we could say a little bit about this sign. As you know, sines and cosines are complementary functions, so sine of 90 minus theta is the same as cosine theta. If you let me take another step here, I could write this for us from the Earth's field. And when I put the cosine together with the sine, I get tangent theta. Your author writes this constant as a capital K, so I'll go ahead and do that also. Because again, our job here today is not to figure out the real total strength of it, but just to figure out how it changes with distance. And so we're going to focus on finding that n. And so we'll never find this k, which we couldn't until we found that also. And so all of these two we're just going to kind of ignore. Then your author says, watch this little fun and tricky math. Oh, let me erase this. Is if you leave tangent theta alone here, so tangent of theta, and you put the constants over the other constant, so this is an unknown constant, and we'll divide it by the force from the Earth, which we'll reasonably assume it's still a constant. And then you have r to the n. This would be saying then that if I were to collect data and as I go for different distances of r, which I'll measure in meters, then I will get different angles, which I guess I will measure in, I guess, degrees. Well, why not? Trying to remember that, yeah, that compass over there has everything in degrees, not radians. All right. Now, my goal then is ultimately to figure out what n is. So when I go to make a plot, I'm going to do this little trick. Let's take this equation and take the log of both sides. So on this part of the equation, I have the log of the tangents of theta. And on the other side, this is where the property of logarithms can come into a real handy. Because if you think about this as a product of these constants in front, and then r to the n, when you take the log of this right-hand side, you can break it into two pieces. And then you could take advantage of another nice property of logarithms. I like to call it the log roll, because you can start with an exponent here and roll it down the log. And so if we do a log roll, we get the n as a coefficient out in front instead of a power. Now I got to admit, when you first look at this looks like a messy equation, but watch this for a moment. If you think about this whole thing being plotted on the y-axis, see the whole thing, not plot theta, not plot tangent of theta, but plot the log of the tangent of theta, and you call that y. And then if you plot this on the x-axis, again, not plotting r on the x-axis, but the log of r on the x-axis, then you would have a number, and then you would have some kind of constant, which you might refer to then as the equation of a line, where the log of these two constants is the y-intercept, and the n that I am looking for would be the slope when I plot it this way. And so that was the neat thing about taking the logarithm. And so in a moment I'm going to collect data with you, and I'm going to get r and theta. But what I'm going to ask for you to do is to take this data and then go to, and again, your choice. Looks like a lot of you are going to graphical analysis. I think a lot of you started with Excel or Google Sheets, but now a lot of you are going to graphical analysis just because it's so user-friendly. But it's your choice. You know, keep sending the emails if you're having troubles getting to graphical analysis. But I think I've gotten most of you on the virtual machine, and so I can send those directions again if you need it, and how to get to the virtual machine, and then you can just select graphical analysis. But you want to just type these in. I will say this: when you go to graphical analysis, the default is in radians. So before you go anywhere, when you start graphical analysis, make sure even before you type them in, although it doesn't matter because we haven't done any calculations yet. But I would encourage you, so you don't forget, before you even type it in, okay, go to the File menu, File, go down to Settings. I think Settings is the third one from the bottom, so it's way down. You click on File and go way down. Third one from the bottom is Settings. Go to Settings, and then a dialog box will come up. And in that dialog box, there is a button you can push or select that says radians or degrees. And you'll see when you first start it, it'll be in radians. Click degrees. It'll really be messed up if you don't change it to degrees. So we're measuring everything in degrees here. All right. So you're going to have a bunch of data here. And like I said, I want to measure these. But once you have that data, you should make two new calculated columns. This one here would be log of r. So again, on the File menu in Graphical Analysis, go up to where it says New Column. And then, or Data, excuse me, it says Data. So click on Data. Then go down and it says New Calculated Column. Select that. You can call it anything you want. It asks for the title first, but then at the bottom it asks for the formula. And this is the formula you want to put in. You want to put in the log of r. Okay? And the syntax has it in double quotes. So you're going to type in something like that, or you can just do the GUI interface and click on the buttons to get the log of r. So you've already made a column for r, and then this is going to be the log of r. Oh, I'm sorry. I got ahead of myself. Tangents first. And so I would make a column that is, no. Sorry. That's what I wanted. Log of r. That is what I wanted. Okay. So that is going to be your x-axis in a minute. All right. So that's the log of r. Now, the other column, you could do it in a couple of steps, but maybe it's easier just to make one big step. Do the same thing. Go up to Data, go New Calculated Column. And again, once you do that, you can call it anything you want, but we want to make this one. So you want to go to where the little button that says Select the Function and select Log. Then select the tangents and then the angle theta. And that is going to be your y-axis. Okay, So again, let me just say it, in a moment we'll start collecting the data. And this is the part I was saying that it makes sense. It's the first lab on magnetism. So this is pretty easy to collect the data. It's actually pretty easy to do the graphs once you get the graphs. Probably the hardest thing is this whole time frame here at the beginning where I explain why are we doing what we're doing. And so like I said, in case you missed it, what we're trying to show is that the field from a monopole, if you could even get a monopole by yourself, and this is our little trick, should be kind of like the electricity where it has the 1 over r squared value. So I'll say it again, I'm going to give you this data. What you need to do is to take that data and type it into graphical analysis and then make these two columns. Then once you make those two columns, you are then going to make a graph. And on the vertical axis, as I said, plot the log of the tangents of theta. And on the x-axis, plot the log of r. And hopefully you will get something like this. I'll come back to this whole point. You will get something that looks like a line, where the slope of that line is what you're looking for. So I should have a slope of -2. And so coming to a graph, a slope of -2 would be something like this. Okay, now, also maybe just to remind you about logarithms, if you remember, the log of 1 is 0. Anything less than 1 is negative, and anything more than 1 is positive. Now the reason I point that out is coming back here when I actually do this experiment in a moment, I'm going to start with my magnet kind of close, 0.1 meters away. That's less than 1. And then I'm going to keep moving it till I get a ½ meter away. I will never get greater than 1 meter. So my graph I made is always going to be down, here. It's always going to be on this side. All these numbers will be negative. I will have the log of distance. And the biggest distance I'm going to have is a ½ meter. That's a negative number. Okay, so my graph's going to be somewhere over in the second and third quadrant. And then likewise, just to remind you a little bit about logarithms and trig functions. Remember, log of 1 is 0. But also remember the tangent of 45 degrees is 1. Okay, so any angles greater than 45 degrees, and we will get some of those, not many, but an angle greater than 45 degrees is going to give me a number greater than 1, and this is going to give me positive values. But most of my angles, this magnet will not tilt it as much as 45 degrees. It'll be something less than 45 degrees. So because of that, most of my data being under 45 degrees means the tangent of that would be less than 1, which means the log of that would be negatives. Okay? So I'm kind of thinking that I'm going to see something roughly like that. Okay? A line, slope of -2. It's all over here in the second and third quadrant. And the big angles are over here in the the big angles are over here where I have a positive value for the vertical one, but most of the other ones are going to be down here. So I think I said that right. So let's see what kind of slope we actually get. Let's give this a try here. So again, let me kind of move around to over here by the equipment, and maybe I'll just go ahead so I don't have to keep walking back and forth to the board. I'm going to make a little chart here, and this will be my R, and this will be my theta. And as I said, I will measure things in meters. I will start at 0.1. And as you see, I'm going to go 1 centimeter at a time. For the first 10 centimeters. Okay, and that'll be my first page. And then R versus theta. Then I'll start going a little bit more, maybe about 4 centimeters per time. So this will be 0.24, 0.28, 0.32, 0.36, 0.40. And then just to round it to the end, I'll go 5 centimeters and 5 more centimeters, and this will be the last of my data. Okay? And so again, all this distance will be in meters, and this will all be in degrees. Okay? All right. Now, looking at my equipment, let me just set it up here. Sadly, my compass tends to stick once in a while, so I'm going to just give it a little wrap here. I think I have everything that is magnetic kind of far away. Good. And so this will kind of show me which way is north. And I'll just kind of line up my compass here so it says 0. And then you can see the meter stick sticking out, so I can measure distances here. It's kind of hard to tell here, but the meter stick is set up so that the 50 centimeter mark, the midway on the meter stick, is right underneath this compass. And so we are at 50 centimeters here. And that means my first reading, I'll put the magnet right here at the 40, because that would be the 0.1 distance away. Okay, so here it is. Here's my big magnet with the North Pole. And as I said, I'll begin. And I'll just bring it close. You can probably see the compass beginning to move. And I'll just place it right there. And maybe tap it a little bit. And so you guys could see it better on camera. I think I moved it too far away from me. Bummer. And but I think I can. Maybe I need to come over on this side. But this was pointing over here and it moved away, and so it looks like I'm at about 66 degrees. So I'll say 66. And then I'll pull it back a little bit. Maybe kind of tap it, see if I can get it to settle in now that I am 11 centimeters away. And maybe can look down a little bit. Looks like I'm about a 62. So here's a 62. Then I'll move a little bit more. I'll do a little tap. And looks like maybe a 57. And so I'll come over here. And maybe that's a 52. And call that. No. I am 14 centimeters away. And I'll call that a 47. Now I'll come here. And I think I'm going to go under 45 degrees. Remember, this was this is the place where my graph would switch from positive to negative. Okay, and it looks like we're at about 43, right in the middle actually. I'll go 43 and a half. 43.5, okay. Let me go to 16. Looks like an even 40. Let me go to 17. And so that looks like about a 36. Actually, it was 36 or 36, and should I call it 36 and a half? I'm going to call it 36 and a half. I'll keep going here. Here's 18. Okay, and so this is a 30, I'll call it 33. Let me go to a 19. I'll call that an even 30. And now we are a total of 20 away, 20 centimeters, and it's like 20, oh, should I call it 28? Or, yeah, call it 28. 28. Okay, continuing on, now we'll go a bigger jump. Let's go to 24 centimeters away. And we're at, looks like 19 degrees. Oh, not a big change. Maybe I shouldn't have gone quite that much already. Well, we're going to have quite a bit of data. So I'm committed here, so I'm going to see where it goes. And then this is 28 here. And so we are at about 9 degrees. $32. Oh, didn't move. I don't like the sight of that. Let me go back to the 28. 28. Because I said 9, but either got stuck or I read it wrong, because that's more of a 13 and a half. All right, so 13 and a half and 32 is where I saw a 10 last time. Yeah, 10 again, and got concerned about my reading. So there's 10. And then 36, I guess would be right here. And so we're looking at about 7.5 degrees. And then the 40, oh, I might be falling off the table here. We're all getting to a small angle, so I'm wondering if I'll even bother to go the rest of it. But we're at 5 degrees. Uh, 45. Maybe I'll do something like this. And so 45. I am at 3 degrees. And one last reading. And I am at, I'll call it 1.5 degrees. All right. So this is half of our data. This is, moving along a westerly direction. Let me turn it towards you. You can read these and hit pause. I won't bother to try to translate them onto the board there. If you can zoom in, Ron, and get those, we'll say, okay, write those number down in your graphical analysis and make the plot. And then hopefully you'll get an n equal to something close to -2. Now, let's do all of this again. Let's go ahead now and move it from the other direction. Because your author suggests that if there was something in this room or something that I'm doing wrong on a regular basis, that the other direction would be off in the other way. And so I got to admit, it's hard to get a -2 for this lab. And so hopefully, when we do the two of them together, the average of our two slopes is a -2. And so let's see what we get. But I got to admit it, this monopole thing is a little bit questionable. So we don't always get things real close to -2. But like I said, let's see what we get here. All right, so I'll put that aside and I'll kind of make myself a new chart here. And so let's do this all again. R and theta. Let's go 0.01, 0.11, 0.12, 0.13, 0.14, 0.15, 0.16, 0.17, 0.18, 0.19, 0.20, 0.24, 0.28, I wonder if I should try to squeeze it all into one page here. 32, 0.36, 0.40, 0.45, 0.50. Okay, so I'll put them all on one page here and say, all right, what angles do I get? And so if the slope of this first one is off from a -2, hopefully this one will be off also in the other way, and so that I'll get an average close to -2. All right, so to do this one, I want to first of all just move this magnet out of the way real far. And let me just bring my compass to this side of the table. Okay? And I'll get on the other side and start. Now, maybe I can stay out of the camera. I'll stay on this side. And then let me just kind of align it. Let me just tap it. Let me turn it so that we start off with the compass pointing magnetic north, or at least, whoops, if it's not magnetic north, it's the same as the background. And some of our compasses are better than others. This one's a little sticky. I probably should have grabbed a better one there. All right, so let's begin here. And I'm afraid that stickiness of this compass may throw things off quite a bit. But anyways, we're this far into it. Let's keep going here. All right. So here is my compass again, and I'm sorry, my magnet, and I'll bring it over, and I will begin by putting it at a distance of 10 centimeters away and tapping it. And it looks like it has gone over about 61 degrees. So I'll call it 61. What did we get last time? Out of curiosity? 66. Okay. And so let me move it to 61. Do a couple taps, and I get about a 56. So 56. What I get last time? Yeah, so we're a few angles lower this time. Maybe that's a good thing. Maybe the average is going to be just about right. Hopefully they're not both wrong, both directions. Okay, so continuing down, this looks like, what I said last one was 56, because this is more like 51 and a half. So 51 and a half. Put it here. And so this is about a 48. You go to 14. That looks like about 44 and a half. 44 and a half. Let me go to 15 here. So that looks like about a 41. Now let me go to 16. Okay. 30, let's call it 37. Let's go to 17. And that looks like about a 33 and a half. Let me go to 18. 31 degrees. Nice. Okay. 19. Be about 28 degrees. And then a distance of 20. And I get about a 20, let's call that 25 and a half. 25 and a half. Now I'll make a big jump here, all the way out to 24, with a big change. And the last time when I jumped out here, it went way down to 19 degrees. And this one's been a little smaller, so yeah, and sure enough, I got 18 degrees. So 18 degrees. And let's go to 28. And so we're looking at about 13 degrees. Okay. Let's go to 32. Yeah, when we're done here, I'm going to maybe clean up the sharp edge on this one. And then this is, let's call it 9.5 degrees. 9.5, which is 32. Okay, well, we're about matched up. So it looks like these are going to have a little slightly different slope. This will have a lower slope than the other one. So hopefully the other one was a little over 2, and this one will be a little under 2, and yay, we'll get a nice average. So be curious. 36 would be right here. And so we're looking at about 8 degrees. 40 would be right here. And we're looking at about 6 degrees. 2 more here. Maybe yeah, it's going to fall off. So let me swing this around. Put it right here. Okay, so there's 45. And I'm looking at about, looks like 3.5 or 4. 3.5. And then finally, last one here at 50 away. Oh yeah, see, yeah, this one went from bigger to smaller. This one has a much steeper slope than that one. Or not much, definitely different slope. And then this is going to be 1, 2, 3 or 2.5. Let's call it 3. Now, that should be interesting. So, plot those two. Let me show you the data so you can see it a little better. And so this is going to be your second and last plot. And so make a slope of that one too. And so again, your job here for the lab is to take this data, now that hopefully it made sense to you, put it into graphical analysis or Excel, whatever, and get the value of n. And you should have it twice, once from the experiment when I was moving along outward towards the west, and this one here where I was moving outward towards the east. Now, real quick before I lose you, let's talk about the discussion questions. And so that's the meat of the lab. In fact, those are the two procedures, the steps of the procedures. But now there's 5 discussion questions. I think I touched on most of them, but I just wanted to double check. The first one says, is it possible to actually isolate a point magnetic monopole like you can with an electrical charge? Well, I think I answered that, so I'll move on here. 2 says the Earth's magnetic field. This is a good one. And this is actually the main reason why I wanted to come back here and show you this. It says actually the Earth's magnetic field is not parallel to the ground's. Does this have an effect? And are we concerned about this in this experiment? Now, this is why I brought what I'll call a dipping compass here. Now, if I were to hold this compass in my hand, and I need to hold it a little bit above the table, in fact, maybe I'll come back over here to the non-magnetic table so you can kind of see what I'm after here. But what I'm after here is if I were to put this compass just on the table here, and hopefully this compass isn't too close to be affecting the two, it'll go along the Earth's magnetic field, or at least the background field. Like I said, we have other things around, so this may not be quite north or south. But watch this. This is going to be important as we try to understand the Earth's magnetic field. If I were to turn this compass in a vertical direction, the compass would actually dip down. And so what this tells me is that the Earth's magnetic field is angled downward. And this one's bent a little bit. It shouldn't bend quite that much down. But again, it's kind of hard to tell. Yeah, that is a lot. I don't think it's this. Let me just grab another one. So you notice that one's a little bit loose, and then sometimes the magnetic fields aren't really along the direction of the material anymore. They get kind of messed up. So let me try this one. This one feels better. Let me see if I can stop it here. Get it aligned. But if I turn this, and you probably remember this from the lecture, the Earth's magnetic field is pretty steep. But I don't believe it should be as steep as that one indicated. Yeah, this one's doing much better. And so this one's going to stabilize maybe right about here. But the point in the lecture, and the point here now, is that the Earth's magnetic field is actually going into the Earth at a huge angle. It's got a huge dipping angle. So it is not just in a flat horizontal plane, but it's dipping down at an angle. Hey, okay, we had another little power problem with our camera. That's not a good sign. I think maybe it's beginning to die and we're having some troubles. But we'll splice this all together and make one of them. So what I was saying when the whole thing collapsed was that the question on the discussion is, does the fact that the Earth's magnetic field angled down, and that's what I was trying to show you, angled, does it really matter? And the answer is no, because the vector, any vector, if we go back to just what you learned in Physics 121, we could think of the Earth's magnetic field of having a horizontal and a vertical component. So the horizontal component would make the compass rotate this way. The vertical component would make it rotate this way, would make it dip. But our equipment, the way it was set up, it could not dip. So the vertical component was irrelevant. It didn't matter if we had a little bit of a vertical component, no vertical component, or a lot of vertical component. The equipment could not detect the vertical component. It only responded to the Earth's horizontal component, as I was showing you with all these drawings and all these diagrams here. So come back to the discussion questions here. And that's probably maybe the toughest one to answer when it says, and I'll just, for my own sake, because it's been about 30 minutes ago, I had to reset the camera there. But the Earth's magnetic field is not parallel to the Earth in Santa Barbara. Is this a concern? And as I just explained, no. And so go ahead and explain it. Here's another good one. I touched on it, but I'll touch on it again. It says, at what distance from the pole of the long magnetic is the size of the Earth's horizontal field equal to the magnetic one? Now, if you come back to this picture, you can kind of see it here mathematically and hopefully conceptually, that if the Earth's field, and I should say now that we just did that one, the horizontal component of the Earth's field and the field from the magnet are equal in magnitude, that would happen right here when these two are equal. These angles would be equal. So that would be 45 degrees. If I looked on this graph over here, 45 degrees, the tangent of 45 is 1 and the log of 1 is 0. So right here where it crosses, this is the position that would be where the Earth's magnetic field, horizontal component of the Earth's magnetic field, and the one from my magnet are equal. And so that's what you're going to do, is scan your graph and see where does it cross right there. But the magical place is to realize that would be at 45 degrees here. And so that's what they're trying to get at in number 3. Number 4 uses a word that I did not use, so I want to touch on it. It says, what is a couple and how was it used in this experiment? Well, let's come back here. Do you remember way back here where I put in this factor of 2? Where I said that this compass would be pushed away from the magnetic force of here, but it would be attracted here. And so what happens here is these two forces are equal. In other words, the net force, not the net torque, let's go back to Physics 121, the net force would be 0. So this magnet that I'm holding in my hand that I was moving back and forth would not push this compass away, nor would it attract it, because it makes two equal and opposite forces. That is what's called a couple. So a couple is equal and opposite forces. So the net force comes out to be 0. So a couple will never make something translate, but it can make them rotate. And that's what we have here. And so these two forces that are equal opposite, they make a couple. They will never move the compass translationally, but they will rotate it. And the Earth can do the same thing. the Earth's magnetic field makes a couple. They're equal and opposite. And so the Earth's magnetic field will never move this compass to the north or to the south or east or the west, but what it will do is it will rotate it. And so that's a couple. So a set of equal and opposite forces. Now, I should say equal and opposite forces on the same object, because if you say that too quickly, it almost sounds like Newton's third law, because Newton's third law says the forces are equal and opposite always, but Newton's third law says on different objects. So the net force on a given object does not come out to be zero, but a couple is a set of equal and opposite forces on the same object. And as a result of that, you get a net force of zero on that object. And the result of that is you don't get translational motion from a couple. You do get rotational motion from a couple. So that's a fancy word. And those of you who are in our statics class, that's, you probably use that word a lot. That's a very common engineering word there. And since your author uses it here, I thought I better point it out. And then finally, I think you can do 5 without me saying anything. This just says, now that you've done your graph, what'd you get for your slope? This is your value of n, and average the two, see what you get. And then it asks you to calculate the percent difference of how close did you get to that -2. And so in an ideal world, we would get -2. Our equipment, all the magnetic fields, and in my case, the sticky compass, I'd be surprised if we're even close to -2. I know in a face-to-face setting, when I go around to help the students, we usually get numbers like -1.7. So if if my sticky compass wasn't too sticky, maybe we're getting kind of that same thing. So don't be too concerned if you're really far away from -2, but at least let me point out that that would be the ideal setting, and we'll just take whatever we get and call it good. And that's the end of it. So we are done with our first lab on magnetism, and next week we'll do another one on magnetism. Take care.